obviously, we are going to start with Neil Bohr's experiment. So in Neil Bohr's experiment, there was a small chamber like a tube light where gas was filled. He tested with mercury vapor. He also tested it with hydrogen. So you have a supply, a power supply right there, and it's connected like that to the gas. Okay. So according to Neil Bohr experiment, he observed that every vapor and gas has a unique pattern. So he concluded that every material used inside the gas tube gave a spectral pattern. Spectral pattern is like colors that come out in form of photons, obviously. Signature to the material. So every pattern he got from different material was unique. All right, so we're going to remember that. So he proposed that the energy is transferred only in certain well-defined quantities. All right, well-defined quantities, and electrons move around orbits, but only in prescribed orbits, like that.
So basically, the gas tube itself produces the pattern, not the gas.
Every element has its own unique pattern inside, or the atomic structure inside. Okay,
So it depends on both of this, what the gas tube is built of and the gas itself.
only the gas. Okay, only the
Right.
gas. Yeah. So this is the most important point. What I'm writing when jumping from one orbit to another with lower energy, a light quantum is emitted. Right, kids? Now, the importance of this theory is that this theory explained why atoms emitted light with fixed wavelengths. So now let me just explain this using the diagram he proposed. Okay. First of all, we need to understand that how to provide energy to an atom. So there are three ways mainly. Number one, heat the atoms. Number two, throw high energy electromagnetic radiations. Number three, provide electrical energy. Alright, kids. These are the three ways you can do that. Now, according to the atomic model itself, I just need to go to the next page. So, you guys, if you're done writing this, please let me know so I can go.
I'm on the jumping one.
Okay, so you can write that. It's all right.
What is a light quantum?
Quantum is the smallest particle of light. Light photon is the same thing as light quantum.
All right.
Sir, can you scroll up for 1 second? I missed something from the last line, from the first paragraph.
Yes, yes. Is it okay?
Yes, thank you, sir.
All right, kids, should I go forward now, please?
Yes, sir.
Sure, sir.
Now going to the next. Bohr atomic model kits. No, it's this. So in the Bohr atomic model, I just want to tell you the minimum, like the smallest energy level is called the ground state. It is called n equals to 1. And then after a big jump, you have another one. Generally, it works like this. Then another one. And subsequently, as you go up and up, the levels keep on decreasing. The size of them. And there could be infinite number of these. Okay. So let me just move it a bit to the side like that. And also would like to straighten them up. Okay, well, this is good. No, okay. Now I just want to tell you the next one, kids, is going to be n equals 2, n equals 3, n equals 4, n equals 5, and n equals infinity. So this one is called the ground state. This is infinite number of possible states. All right. If the electrons jump from one to this, they basically end up in high. They end up in high energy. Oh my god. High energy states. And then if they come down from this, so jump down, that's basically going from, they end up going to low energy states. All right, is it clear, everyone? So the lowest state is basically the ground state, and the gap between each state, this, it's called a quantum gap. In quantum gap, electrons cannot stay there. Okay, they can only stay between states. This, what you see, is called quantized model of an atom, like that. So, so we can basically write about this that an energy structure of atom was given by Neil. He suggested that every atom has a unique quantized energy structure and has infinite number of energy states, like that, or you could write levels. That's even better. Okay. Then says when an electron absorbs energy corresponding to difference between two levels, it jumps to an excited state from ground state. So let's suppose if N2 will have a certain energy that it requires for something jump from ground state. So if that energy is available, electron will make the jump. Okay, it's very simple like that. So now this is the most important point. An electron in any atom will absorb a photon only if, and this is important, only if the size of photon energy corresponds to energy of quantized gap. So you guys need to remember that. Otherwise, it will not absorb. Okay. You can write this. Give me 1 minute, please. Okay, I'm sorry about that. All right. Is there anything you'd like to ask me? Please do. Okay. Now, kids sometimes no, they're more like interested in asking us. Well, it's not required by the course itself, but just for your general knowledge, if it ever comes in MD CAT, or maybe you're giving some university test, just write that this quantized structure, the energy between these gaps can be calculated with this value, this formula, minus 13.6 z square over n square EV. So it will give you an EV, where the z and n are basically sort of If you look at the X, any element, it has atomic number and the proton number like that. So you can put it inside Z, and then for every energy gap, for n value, you can find the state. Is it clear, everyone? This is just for your own information, for the tests of universities. Otherwise, it's not required by this syllabus. Anyway, now to make matters like more practical, we're going to look at hydrogen quantized model. So I'm going to copy this. I don't want to draw it again. So when you calculate all the energy of different levels, you would be, for hydrogen, it comes out to be something like this. Oh my god. It is, it's minus 13.6 EV, minus 3.4 EV. This one is minus 1.51 EV. This one is 0.85 EV. And this one is minus 0.544 EV. They're going to give you these numbers themselves, so you don't have to worry about that. Electrons jumps are made. Suppose electron absorbs a photon and it ends up at a position right at this one. All right, so here we have an electron. Now electrons cannot stay there for very long. So what they do is they start making jumps back to the energy ground state. So there are a couple of ways they can do that. First, they can make a jump, like they can make partial jumps, like they can go from N4 to N3. And while they're doing this, they're going to release a photon. Then they can also make a jump from 2 to 3 to 2 in the second step, and they're going to release a photon along with it according to the energy gap. And then they can make a jump from here to N2 to the ground state, and they will release a photon. Alternatively, when they jump from N3, they can also jump from 3 direct to 1. It's not a requirement that they will always make a jump from like 4 to 3, 3 to 2. They can jump from any place directly to that. So it can do that. They can also do this, that they can jump from 4 to 2. So this is like a possibility of fifth type of photons being released from 4 to 2 and then 2 to 1. And it is also possible that they directly jump from 4 to the ground state. So in this, if the electron jumps to, let's suppose, 4, or staying at 4, from 4, there are 6 possible photons that might be released when it comes back to the original state. Understood, kids? So whatever it's doing, you guys need to know, it's all random. It's not like you cannot control this. Just want to tell you that law of conservation of energy is always followed in this. So now we need to answer this question where it says, how can electrons move from an excited state to the ground state, like that. So in that case, just remember, If they ask you, you're just gonna write like 3 mark, 4 mark thing. So you say that the the excited state of an electron can only last for 8 to 10 milliseconds. It's that small. After that, they have to move. They have to move down as they cannot remain excited for very long, like that. Now, kids, I just want to tell you that electrons may release energy, number one, directly, or in step by step variation, which means they can come like jump from one to another and then another, or they can jump directly from the where they are to the ground state. So it releases energy in form of photons whenever it comes down, like that. All right, kids, any questions? Please let me know. Write it down, please. I just need to get some tea. I'll be back in 1 minute. All right, kids. All right. Now going to the next. If you guys have any questions now, please let me know. So the point is that how do we calculate or know what type of photons are released when this happens? Okay. So we're going to do a question regarding this and see what happens. Okay. So I'm just going to write an example and let's do it together. I'm going to do one of these. You guys need to do the rest and then you can compare. So let's assume that an electron jumps from ground state, which is n equals 1, to ground state from state 2, sorry, to n equals to 3 by absorbing energy. So we want to know that what are the possible photons released after going back to ground state. All right. So first of all, they have given you the states like this, like that. This will be n equals 1, n equals 2, n equals to 3. They've also given you the values of each of these. The reason why they're in negative, because that shows you that as you go above, the energy increases and the minimum energy will be negative, right? So at infinity it will be 0. They're saying electron exists at 3 and now it wants to make the jump. First of all, we should understand to know what kind of jumps it can make. First, it can go directly. If it goes directly, obviously, from 3 to 1, it will release a type of photon. It can also jump from 3 to 2, and then from here, it can also jump from 3 to 1 to go back. So, either step by step or direct. Now, first of all, I'm going to show you how to calculate energy of the first one, which is 3 to 1 jump. So you're going to find the change in energy. Always do bigger minus smaller, because the bigger number is minus 1.51 and then minus 13.1, 13.6, sorry. And this is all in EV. So you're going to end up with 12.09 EV, like that. Then to convert it, you have to go back to AS. EV is equivalent to, if you do not remember,
1.6 times 10 is per minus 19 joules.
yes, so it's going to be 12.09 times 10 raised to 1.6 into 10 raised to minus 19 joules. This will give you about 1.93 times 10 raised to power 18 minus 18 joules. Once you have the energy in there, then you can write photon energy is equal to hc over lambda. And lambda then will be equal to 6.63 times 10 raised to minus 34, that is the Planck constant, multiplied by 3.0 into 10 raised to 8, and then divided by energy, which is, we just found 1.93 times 10 raised to minus 18. So what you get is about 103 nanometers. You can check. And this particular light belongs to UV range. So this is the UV photon that was released and it makes that jump. Now for the rest of these, there are two jumps. first jump, as you guys can see. The second jump is from 3 to 2, and then the other jump is from 2 to 1. I want you guys to work it out and give me the answer for both of them. Super easy.
1.89 and 10.2 electron volts respectively.
Yes, 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 that's correct. So you can find the change and then quickly tell me the wavelength only. You're not required to write which light photon it is. I'll tell you that in any case. All right, quickly, please.
Done. The step-by-step photons of either of 658 nanometer and 122 nanometer. Sir, are you there?
Yes, why not?
I found the final wavelength 658 nanometer and 122 nanometer.
Yes, that is correct. Everybody else got the same? Okay.
So do I leave?
Yes, you can. So now just wanna show you how it's done.
Okay, sir, Allah Hafiz.
Hafiz. So this is going to be like you guys need to do it 1.51 minus 3.4 and then EV. And then when you have this, you got to multiply this whole thing, like this whole thing, with 1.6 into 10 raised to minus 19. That would give you some energy. And then that energy will be 3.024. So you can confirm this, please. And then when you use lambda equals to 6.63 times 10 raised to minus 34, and then multiply by 3.0 times 10 raised to 8 divided by 3.024 times 10 raised to minus 19. This will give you about 657 nanometer, which is a spectrum of red light, for the domain of red light. For the other one, you guys need to do minus 3.4 minus 13.6 and multiply by 1.6 times 10 raised to minus 19. This will be equal to 2.72 times 10 raised to minus 18. You do the same thing, and at the end, you should be getting 122 nanometer, which is UV light, all right, as well. Okay, Huda, Ryan, Zainab, Aisha, is that clear?
Yes, sir.
Yes, sir.
All right, so this would be the end of the class then.